Hello and welcome back to Math Class in Session. Let's round out our unit on curve sketching with an algorithm for curve sketching. Just remembering what it is that we've studied so far about sketching curves. Here's a curve, and we know that to get these points, we set the function equation equal to 0 and solve, possibly by factoring. To get these points, we set the derivative equal to 0 and solve, possibly by factoring. These are the extreme points. And to get the points of inflection, these points, we set the second derivative equal to 0 and solve. That's what we've done lately with curves. Now let's put a lot of our activities together into something called an algorithm for curve sketching, which is just really a collection of activities that we can do with a curve to gather some information about it so that we can make the sketch of it. We could find the intercepts, the x-intercept, set y equal to 0. For the y-intercept, set x equal to 0. We could get asymptotes. For vertical asymptotes, look for denominators. For horizontal asymptotes, look for limits at infinity. And same with oblique asymptotes. For domain, this will be interesting for us, so we should be aware of the domain of a function if we're going to try to sketch it. And then our first derivative line gives us information about the curve, intervals of increase and decrease, and extreme points. And our second derivative gives us more information about the curve, its concavity and its points of inflection. Taken as a whole, this is called an algorithm for curve sketching, a collection of activities that helps us gather information about the graph of a curve. Let's do an example. Let's graph this function. It's a polynomial function, and it's a fifth degree polynomial. Solution. Use the algorithm. Let's start with intercepts. Well, to get the x-intercepts, we'll have to set y equal to 0 and solve, and factoring is good for that. Solutions to setting y equal to 0 will be x equals 0 or plus or minus 2. And so x is 0 or plus or minus 2. And meanwhile, y, of course, is 0 in each case because we set y equal to 0. And by the way, 0, 0 also functions as our y-intercept. It's interesting to note that any function can only have one y-intercept. It can have several x-intercepts, like this one does. Asymptotes, there are none, because there's no limits at infinity. There's no restrictions on the domain. Domain, there is no restrictions on the domain. Prime line, well, let's differentiate. And when we set it equal to 0, we'll have to factor. And the results of setting it equal to 0 when you solve it will be x equals 0 or plus or minus the square root of 12 over 5, which is the square root of 1.4, which I did on a calculator and got 1.55. So plus or minus 1.55 and the 0 from here. Evaluating the intervals along this prime line, do it for yourself and confirm that yes, it goes plus, minus, minus, plus. Take any one of them. Let's say this one. If I subbed in 1 to the prime, this would be 1 squared is 1. This would be 5 minus 12, so it would be a positive times a negative. That's where this negative sign came from. And confirm the other three for yourself. That's our prime line done. And we notice that it leads us to a maximum point here and a minimum point there. So we have a maximum at negative 1.6. I rounded this even further because if we're going to graph, it's going to be difficult to graph 1.55 exactly. So the max point is negative 1.6, and the y value comes from subbing into the original, of course. And the minimum value, we recognize this first derivative line. It's decreasing to it and then increasing. That makes this a minimum. So a minimum at 1.6, rounded, and negative 5.9, the result of subbing in 1.6 to the original function. Double prime line, differentiate the derivative, set it equal to 0, factor it, of course, and we get some solutions here, some critical numbers for our double prime line. X is 0, or plus or minus the square root of 6 over 5, which a calculator told me was negative 1.1 and positive 1.1. Evaluating the intervals, they look like this. And we can pick any one just to confirm. Let's pick this one. A number between 0 and negative 1.1 is negative 1. Subbing it in here, that makes this factor negative. Subbing it in here, that makes this 5 minus 6, which is negative. And a negative times a negative is this plus sign here, positive. So the whole interval is positive. And I did it for all the intervals, and I suggest that you confirm each one. This leads us to points of inflection, because whenever the concavity changes, there's a point of inflection. So we have these points of inflection. To get the y values, take the x values and plug them into the original function up here. I know they're points of inflection because this is the second derivative line, and I can tell that the concavity is changing as we transit through the critical numbers on the double prime line. Now notice, there's a lot of work shown here, and there may be even more work not shown. And if a student is attempting to graph a function like this and does all this work, it can be a little bit overwhelming. That's why I put the results of the work in boxes. So when I go to graph, I just look at the contents of the boxes. I'll need this. I'll need the prime line. I'll need the fact that this is a max and a min. That's why I put them in a box. I'll need my points of inflection. That's why I put them in a box. And the double prime line as well for concavity. So just bringing the pertinent stuff forward for the graph. The results of all our work. Here's our graph. Here's our chart. And now 0, 0 has to go on it. There it is. 2, 0 has to go on it. There it is. Negative 2, 0 has to go on it. There it is. There's a max at negative 1.65.9. So I put negative 1.65.9 here, the point, and the little curly thing to remind me that this is a maximum. That's what that little symbol means. And there's a minimum at 1.6, negative 5.9. Place it there, again with its little symbol indicating it's a minimum. Our points of inflection must go on. So negative 1.1, 3.7. 0, 0 is already there. And 1.1, negative 3.7. And now reading our prime line. We increase to this point, and then we decrease. So we'll come up through this x-intercept all the way to this point, and then we decrease. Meanwhile, we are going as we approach this point of inflection, we are concave down and upside down soup bowl, becoming a right side up soup bowl. So it will come up, over, and then become a right side up soup bowl, and then an upside down soup bowl, because this is a point of inflection, and then a right side up soup bowl again, reach a minimum, turn, go up through the x-intercept, and on to infinity. Draw it as best you can and label your graph. And it all came from the results of our work done previously. Let's do this again. Graph the function. Solution, use the algorithm. Intercepts. Well, let x be 0. That means y is 0. So there's an intercept at 0, 0, that's for sure. And where else is there a 0? Well, if x was 2, we'd have square root 2 minus 2, and that would be a 0 factor here. So x can be 2. There's our intercepts. Now remember, there can only be one y-intercept, and here it is. It's the origin. Y-intercepts are any place where x equals 0, and that can only happen once in a function. The domain, well, we see a root sign. So that means the radicand must be greater than or equal to 0. So set the radicand greater than or equal to 0 and simplify that. And we have x has to be less than or equal to 2. When you solve this inequality, x is less than or equal to 2. And notice I put it in a box. Intercepts, domain, asymptotes, there are none, because there's no limits at infinity. As x grows large, well, x can't grow large because its domain stops at 2. X has to be less than 2. But as x grows large and negative, we have a large negative times the square root, which is always positive. So this will become large and negative as well. So we have no asymptotes, no limits at infinity, no restrictions on the domain in denominators. So we can continue with a prime line. Differentiating. This is where a responsible student will pause the video and confirm that yes, this is the derivative of this. Do the work yourself. Setting that derivative equal to 0, we get 4/3 and 2. Notice how this particular prime line doesn't have an arrow on the end here because its domain stops at the number 2. That's why there's a 2 here on the end. And the only critical number is set 4 minus 3x equal to 0 and solve, because when you set the prime equal to 0, set the numerator equal to 0 and solve, and x turns out to be 4/3. This is our prime line, subbing in with something large and negative. The denominator is always positive. The numerator will be positive. Subbing in something greater than 4/3 in as well, the denominator will definitely be positive, but it looks like the numerator will be negative because we're subbing in something greater than 4/3, like say 5/3. And if you subbed in 5/3 here, we'd have 4 minus 5, and that's negative, the denominator being positive. So we found a maximum point. It increases to it and then decreases from it. So we have a maximum point. 4/3 is 1.333. Plugging it in here to get the y value of 1.1, rounding off because we are graphing. Double prime line. Now you have to prime the prime. And I'll do it. I'll present the result here, and you'll pause the video and confirm that yes, this is the result of differentiating the derivative, the double prime. Setting it equal to 0, we can see that x equals 8/3. If the numerator were 0, x would be 8/3, but 8/3 is bigger than 2. So there are no critical numbers here. And so for our double prime line, we can see that this double prime is always negative. Because if x has to be less than 2, anything you sub in here makes this numerator negative. Try any number. 0, -8. -50, so you got -158. It will always be negative. So it's always concave down because the double derivative is always negative, and there will be no inflection points. So carrying all the boxes forward. 0, 0 has to go on the graph, place it on the graph. 2, 0 has to go on the graph, place it on the graph. And we've got a max point at 1.3, 1.1. So let's see, 1.3 is right here, up to 1.1, which is right there. We have a max point, labeled with the little curly thing to indicate that it's a maximum. And we see we increase until we reach our maximum and then decrease and then stop at 2. So we know the graph must come up through the intercept, obey the maximum, and then come back and stop here. Draw the graph, label it, and move on. A third example, graph the function. Solution, use the algorithm, of course. Intercepts. Let's start with the y-intercept. To get the y-intercept, sub in 0 for x. That's how you always get a y-intercept. Sub in 0 for x. And we have 5/9. 5/9 is 0.555, which is, we'll round to 0.6. So our our y-intercept is 0.6, and for the x-intercept, set y equal to 0, which means this numerator has to be 0, which means x is plus or minus 1. Intercepts of a function. Domain, well, denominators can't be 0, so x can't be plus or minus 3/2. Because when you drag the minus 9 across and divide by 4 and then take the square root, you get plus or minus 3/2. So x cannot be plus or minus 1.5, which is 3/2. Asymptotes, they come from restrictions on the domain. So vertical asymptotes at x equals plus or minus 1.5, that will be the vertical asymptotes. Horizontal asymptote are the limits at infinity, and we know we're supposed to pay attention to the highest exponent on x that we see, and that's 5 over 4, which is 1.25. So horizontal asymptote y equals 1.25, and vertical asymptotes already mentioned, plus or minus 1.5. Putting them in a box, because they're going on our graph. We've got our intercepts, and we have our asymptotes. Prime line, well, we have to differentiate. I've done it here, and I strongly recommend that you pause the video and do it yourself. Don't take my word for it. I can see there's a critical number when x equals 0, and I can see there's a restriction when x equals plus or minus 3/2. So 0 plus or minus 1.5, which is 3/2, goes on our prime line. Evaluating the intervals, that is, we can see the denominator is always positive, so substituting in something large and negative, we get a negative times a negative is a positive. Subbing in -1, we get a positive. Subbing in 1, we get a negative. Subbing in something large and positive, we get a negative. Understanding that the plus or minus 1.5 are asymptotes, we've only found one point of interest here. It's a maximum when x equals 0. And we can look up here and see, there it is there, x equals 0 and 0.6. We've already found this point, but now we know that that point is a local maximum from the prime line. Putting it in a box, of course, because everything that goes in the box is going onto the grid, onto the graph. Double prime line, now here we go. I'll differentiate this. You will pause the video and do it yourself and confirm. This is the double prime. It's a good little exercise. And we can see the numerator is always positive and never 0. So the only thing that's going on our double prime line are the restrictions here, plus or minus 3/2. Evaluating the intervals we get, confirm it. If I subbed in 0, for example, the numerator is always positive. The denominator would be -9 cubed if I subbed in 0 for x, which is in this interval. So that's why there's a negative sign here. And if I subbed in something large and positive, I think you can evaluate this as positive. It's concave up for wherever we see the plus signs, and concave down for wherever we see this negative sign. That'll need a box because it's going on our grid. So all the boxes and prime lines get carried forward. They're the things we pay attention to when we make the graph. So bringing them close to the graph paper and simply obeying all the boxes. 0, 0.6. Let's find that. 0, 0.6. Looks like there's a point right there, and so on. A point at 1, 0. So there's 1. A point at -1, 0. So there's a point. There's a maximum at 0.0, 0.6. So this is an intercept, but it's also a maximum. So let's label it as such. Horizontal asymptotes at y equals 1.25. That's our limits at infinity. 1.25 is between 1 and 1.5, so right about there's a horizontal asymptote, and one here as x approaches positive infinity as well. Vertical asymptotes at x equals plus or minus 1.5. Okay, let's go to negative 1.5. There it is, and draw a vertical asymptote there. And let's go to positive 1.5, which is over here. Draw a line and make an asymptote happen there. So we have on the graph, on the graph, on the graph, on the graph, on the graph. All of these boxes are on the graph. And all we have to do is pay attention to and obey the asymptotes and the prime lines. So this is an increasing function, and it's concave up to the left of negative 1.5. So if I'm examining this part of the graph, I can see that it's increasing and concave up and obeying these asymptotes. So it must be climbing up here, concave up, like a right side up soup bowl. It must be. Then, after the asymptote, it's increasing to its maximum and then decreasing. So it must be coming up from the depths, through the intercept, through the maximum, turning back, and then coming back down. And then beyond 1.5, let's look at the concavity. As x is greater than 1.5, it's concave up. So it's a right side up soup bowl to the right of this asymptote, and it's decreasing. So it's a decreasing right side up soup bowl obeying the asymptotes. So if we obey the boxes, we'll get the right graph.